Here we go. We're recording. So welcome back, everybody. This is week 13 of class. We're really getting towards the end now. And what we're going to do today is finish up this lecture, which is on magnetic fields and forces. All right, so we'll be done with this by the end of the day. Then on Wednesday, we're going to start a new lecture on sources of magnetic fields. Okay? So the picture so far is we kind of have a sense of what a magnetic field is and what it can do. We've seen it can exert forces on moving charges. In the next chapter, we're going to actually be able to calculate magnetic fields, how strong they are, what direction they're pointing in. That's going to look pretty familiar because we did similar sorts of things with electric fields way at the beginning of class. All right? So a few things. We have the next homework assignment that's due next Monday. There's a worksheet. The worksheet is a bit longer than usual, but we only have 3 problems from the book. So that's going to be due next Monday. Any questions on that? All right, so let's get back into the lecture. So as I already said, we've covered in this lecture how magnetic fields can exert forces. That could be a force on a single moving charge that's just traveling through the B field, or a force on a wire, which contains a whole bunch of moving charges. What I want to show you today is that magnetic fields can also exert a torque. All right? So what we're going to start off with is a review of torque. This is something we learned about back in Physics 45, but we haven't really talked about it too much in this class, so I think it's worth just going through again. All right, one thing to remember about torque is that it's given by a cross product. And like all cross products, there's a sort of right-hand rule involved with figuring out the direction. So torque is basically the rotational analog of force. We think of force as something that's necessary to get an object that's not moving to start moving. You have to apply a force to it. In a similar way, if you have an object that's not rotating and you want to get it to start rotating, you're going to have to apply a torque to it. That's what we mean by it's the rotational analog of force. But it's a little bit more complicated than force. Okay? So here's how we want to think about torque. First of all, we have some kind of object that we're applying the torque to. In this picture, I'm imagining the object as a baseball bat, but obviously the object can be anything at all. So on this object, we're going to label the axis of rotation. That's basically the pivot point where the object can swing around. So if you want to imagine something, you can imagine like drilling a hole right there where the red X is, and putting a little pivot around there, like sort of driving a little rod through there so the bat can pivot around that point. Okay, so that's our axis of rotation. In green, this is the point where we are applying a force, all right? And that force is given by this vector F right here. So that's one vector we want to be thinking about as the force. Another vector we want to think about is this one right here, R. What is R doing? It's going from the axis of rotation and then straight out to the point where the force is applied. Right? So R is just a vector that takes you from the axis of rotation to the point where the force is applied. And if we want to get the torque, it's just R cross F. R cross F, that's all there is to it. Okay, so as far as the direction goes, there's a right-hand rule. The same right-hand rule applies for all sorts of cross products. Remember, you take the fingers of your right hand and you point them in the direction of the first vector. That's R in this case, right? So I'm going to go like this, point along the direction of R. Then I'm going to curl this way in the direction of F, right? So in this case, my thumb is going into the page. Here's what you want to think about the meaning of that direction, okay? My thumb kind of represents the axis which we're rotating about. And my fingers are showing us the direction we're going to start rotating if we apply this torque, right? So in this case, it's a clockwise type of rotation. You see that? If my torque were going in the other direction, that would show us a counterclockwise type of rotation, which we're inducing. All right. So like all cross products, we can find the magnitude just by taking the magnitude of the first vector times the magnitude of the second vector times sine of the angle between them. So you see on the diagram, theta is the angle between our R vector and our F vector. So if we just take RF sine theta, that gives us the magnitude of the torque. And we can clearly see that because there's a sine theta factor, the biggest possible torque is going to occur when you apply the force at a 90-degree angle, right? That's why when you try to open a door, you apply at a 90-degree angle to your R vector. You don't push into the hinges. That's not going to open the door, right? Okay, so there you have it. And all this sort of comes together in the rotational analog of Newton's second law. Of course, we know that the net force on an object is equal to mass times acceleration. You guys remember from physics 45, there's like a rotational version of that same equation. This says the net torque that acts on an object, so we sum over the tau vectors, tau is for torque, that equals I times A, sorry, alpha, not A. So again, this is the net torque on this side. This is what we call the moment of inertia, I. And alpha is what we call the angular acceleration. So it's not just a normal acceleration in meters per second squared, right? It's an angular acceleration in radians per second squared, okay? So I know I'm going through this kind of fast, but hopefully all of this is a review for you guys. You should have seen this back in 45, okay? So those are just some things I want you to have in the back of your mind as we keep going through this. And just to give you a little practice, I want you to try this one out, okay? So this is our object. That's our pivot point. So again, imagine there's just like a hole drilled right there, and we sort of fit it onto an axle right at that point. And we apply a force of 25 newtons right here, 32 centimeters away from the pivot point. And the angle at which we apply the force right there is 35 degrees. So I want you to tell me, what is the torque? Give me both the magnitude of the torque and the direction. Okay, so try to work this out and see what you get. Remember R cross F. R cross F. All right, let's start with this, everybody. What's the direction?
Negative z direction.
Do we agree? Negative z? All right, let's just go through that process, right? The R vector, we're doing R cross F. Our F vector is the force, so that's the one that's going straight to the right. The R vector is the one that takes us from the pivot point to this point where the force is being applied. So it's actually exactly like what I just showed you, right? R goes this way, you cross with F, now your thumb is going into the page. So into the page, in the standard coordinate system that we'll use, is the negative z direction, because we have x, y on the plane of the page, positive z coming out of the page. So if we're going into the page, that would be negative z, okay? That's just the standard coordinate system we'll use. And just like before, this is indicating that it's inducing a kind of clockwise rotation, right? If we were to just take the situation as is and apply this torque, we'd get something going clockwise. So that's the direction. What's the magnitude? What are we getting?
4.58 meters.
Yeah, 4.59-ish Newton meters. So here, let's just do it real quick. This is our R vector. This is our F vector. The torque is equal to R cross F. We found through the right-hand rule that the direction is into the page, which is the minus z direction. That's the convention. Okay, so the magnitude of this torque is going to be given by, let's take R, let's take F, and then sine of the angle between them. So R is just the straight distance between the pivot point and the point where the force is applied. That was 32 centimeters, or 0.32 meters. The force, 320 actually, sig figs. The force was 25 newtons, and then that angle was 35 degrees. So yeah, this came out to 4.59. Newton meters are the units, by the way, for torque. Okay, so I just want you to keep that in mind. It's a force distance sort of calculation, force times distance. So we're going to have units of newtons multiplying units of meters. Okay, so to write this as a full-fledged vector, I would just say tau as a vector is minus 4.59 Newton meters k hat. That indicates we're in the negative z direction. Okay? So pretty straightforward so far. Okay, so let's keep it moving. And now let's just take this general idea of torque and see how it applies in this situation, okay? So we're going to do a derivation for a loop of current, okay? In this case, I'm imagining the loop has a rectangular shape to it. But as it turns out, the result we derive is totally general. Doesn't matter if it's a circular loop or a rectangular loop or whatever you want. The result that we're going to get is totally general. It's just a little easier to get there using this setup, okay? So keep that in mind as we go. All right, so here's the setup. We have this rectangular loop of wire. The height of the wire is h. So there's our h distance right there. The width is w right here. And for the time being, we're going to imagine that this loop lies in the xy plane. The loop also carries a current. So just imagine there's a current going all around the loop. In this case, we'll imagine it's clockwise. Okay? So we're also going to imagine that on top of this, we have a magnetic field. So in other words, this loop, which has this current going through it, is inside of a magnetic field, which we will show as going to the right or the positive x direction. Okay? So here's what we're going to do. We're going to break this loop into these 4 different segments. We've got segment 1 on the very top. We've got segment 2, we've got segment 3, and segment 4 like this, going around the loop. For each one of those segments, we are going to calculate the force that's acting on that segment. Okay? Then, once we understand all of the forces on all of those different segments of wire, we can then calculate the torque. Because remember, once we have F, torque is just R cross F. So that'll be the next step. But for now, let's just think about force. We know that the force on a straight segment of wire that has a current running through it, and that's inside of a B field, is given by IL cross B. So all we're doing here for each of these segments of wire, we're applying IL cross B. Okay? Let's start with the first segment. Can anyone tell me, for segment number 1, if we do IL cross B, what are we going to get?
0.
We are going to get 0. Okay, let me just remind you how this works. We'll just do a quick thing on paper. So if force is equal to IL cross B, there's a cross product there, so we know the magnitude of this force is given by ILB sine theta, where theta, in this case, represents the angle between the B field and the direction our current is flowing. Okay? So in this first example, we're trying to find F1. What was the angle between the current and the B field?
It's 0.
It was a 0 degree angle, right? It's just ILB sine 0, which of course is going to give us 0. All right? That is to say, if we go back to the picture, since the current and the B field are going in the same exact direction, if you take the cross product, you get 0, okay? That's how cross products work. All right, so that's our first result. Now let's look at the second segment of wire. Is this going to have 0 force acting on it?
No.
No, because now what is the angle between our B field and our current direction?
90.
Now it's a 90-degree angle, right? So remember, with cross products, if there's a 0-degree angle between the two vectors, you get 0. If there's a 90-degree angle, you actually get the maximum possible value out, right? Because it's like sine 90 is 1, right? So we'll deal with the magnitude in a second, but let's get the direction, right? If we just do the right-hand rule, we can figure it out. For number 2, L, our first vector, is going straight down, okay? Because L represents the direction of the current. And B is going straight to the right. So here, try this. Take your right hand, point your fingers straight down like this, that's L, and then curl them like this, that's B, out of the page, right? So we agree this force right here would be out of the page? All right, and what would the strength of that force be? Well, we have current I. Now for the length of this segment, that's actually what we're calling H, right? H is the height, that's the total length right here. So if I want to write this all the way out, I can write this as HIB, because the length of that segment of wire is what we're calling H. To denote that it's out of the page, I'm going to put plus K hat alongside that. Does that make sense? All right. Now let's do segment number 3. What can you tell me about the force on that segment? That's going to be 0 as well, right? In this case, what is the angle between our B field and our current? What is it? 180, right? And as we remember, you take sine of 180, you still get 0. So if we have a cross product of these two vectors here, we're going to get 0. So F3 is 0. Okay, what about F4? Let's work that one out. Let's do the direction. So we have, take your right hand, point your fingers up, because that's the direction the current's going. And then we will curl them this way. And it looks like now my thumb's going into the page, right? So I have a force on segment number 4, which is going into the page. Okay? And as far as the magnitude of it, it's still H times I times B, because that's the length H, still current I, still B field strength B. But again, I want to show that's going into the page. So I'll write F4 as minus HIB K hat. Okay. Now again, just try to picture what's going to happen here. I hope you can already see that we have a torque happening. Okay? Because on this side, we have a force coming out of the page like this. And on this side, we have a force going into the page like this. So if you think about the combined effects, it's going to start rotating. Okay? So the overall effect is to induce rotation. And now what we want to figure out is, okay, what is a formula for the torque? It's starting to get kind of complicated. We're going to keep going with this, see if we can find a formula for the torque. And as it turns out, at the end, we'll get a simplified expression. Okay? So just follow along for the next couple steps. All right, so hopefully you agree. This is our picture. We have F2 coming out of the page. Remember, whenever I'm trying to show a vector coming out of the page, I show it like this. A little dot with a circle around it. That's meant to bring to mind an arrow coming at you. Okay? F4 going into the page, that's our symbol for that. All right, so how can we bring torque into play? R cross F is the definition of torque. So essentially what we're going to do here, everybody, is we're going to apply that definition of torque to each one of our segments. And then we'll add them all up, and we'll get the total amount of torque. Okay? That makes sense? And, okay, when it comes to torque, we need to think about what is our rotation axis. Hopefully it's pretty clear that we're rotating about this axis, just from what I showed you before. So with that in mind, let's try to figure out each torque, all right? All right, what about segment number 1? Would there be any torque there? No, of course not. I mean, there's no force on segment number 1, so there's no torque. That's pretty much automatic, right? On segment number 2, do we have a torque? Of course we do. Let's figure it out. All right, remember how the R vector works. It goes from the axis of rotation to the point where the force is applied. So it should be going from here all the way out to here, right? But for this force, our R vector would be going out from here to here. All right, so I'm going to draw that for you on paper because this is already getting a little bit cluttered. So let's do that real quick. All right, so here's what you should be thinking. Here is our loop. Here is our axis like this. And you agree we only have to really consider segments 2 and 4 because the others have 0 torque. Remember, segment number 2 has F2 coming out like this. That means R2 is going like this, going from the axis to where that force is, okay? And then we have F4 on this side. R4 is going to be going like this, from the axis to where that force is, okay? And for each one, if you want to find the torque, remember that's R cross F. So we really have to just consider 2 and 4. We'll do those in order, all right? Let's start with number 2. Okay, let's take the right hand, point fingers of the right hand in the direction of R. That's this way. Now I have to curl them in the direction of F. That's this way. I'm not going to break my fingers and try that. No, I have to turn my hand around to do this, right? So which way is my thumb going? It's going down. That's meant to bring to mind this type of rotation right here, okay? So down, if we draw the coordinates that we were using, is actually negative y. So the direction is negative y. The magnitude, well, let's think about it. It's going to be the distance R2 times that force times the sine of the angle between this vector and that vector. What can I say about the angle between this vector and that vector?
Should be 90, right?
It should be 90, yeah. Okay, look, if this vector is on the page, and this one's coming right out of the page, think about that. That's a 90-degree angle between them, okay? That's always going to be the case if you have one vector out of the page and another vector on the page, okay? So here, this distance R2, by the way, since we're calling the width across W, that would be W over 2, right? Make sense? All right. And then what did we say the force was? That was I times H times B, right? So overall, we have a half times W times H times I times B. Okay? Let's do it for number 4. Let's do the direction. So we're doing R cross F once again, right? So R is going this way. Point my fingers this way. Curl my fingers in the direction of the force into the page. My thumb is still going down. So although the forces act in different directions, the torques actually just complement each other, right? That's what we'd expect. They induce the same kind of rotation. So direction is still minus y, and we could go through the work, but the magnitude of this torque is exactly the same. It's just 1/2 WHIB. Okay, so they both have this magnitude, half WHIB, and they both go in the minus y direction. Okay, that's what we found. So let's take a look. For torque 2, remember, half WHIB but we're in the negative y direction, so we can put a minus j hat to indicate that, okay? For number 3, we have 0 torque, because this doesn't even have any force acting on it, so of course there's no torque there, right? And then for number 4, same as for number 2, okay? So let's try adding these together. If you just add them together, we'll just get rid of the 1/2 factor, right? Should be pretty straightforward, just half plus a half. The total torque is just minus WHIB in the negative y direction, okay? So I want you to notice something here. What is H times W? That's the height of the loop times the width of the loop, right? That's just the area of the loop, if you think about it. Width times height for a rectangular shape is nothing more than the area, okay? So what we're going to do is just replace this with capital A for area. So now we have minus A, IB, J hat, once we've done that. Make sense? All right, the next thing I want to point out about this result here is that this represents the maximum possible torque. We've set things up so that my R vector and my F vector are at exactly 90 degrees to one another, okay? It doesn't generally have to be that way. This is a special case, okay? So what you want to think of this as is the maximum torque when the R and F vectors are at 90 degrees. In general, it can be less than this. So I'm not going to do this in the most rigorous possible way. I just want you to notice something, okay? Maximum torque is basically when vectors are at 90 degrees. If they're not at 90 degrees, we generally have a sine theta factor in front, okay? So basically, for a more general expression, we're just going to put a sine theta factor in front of there, and that will generally hold true, not just in the special case, okay? So far we've only considered the theta equals 90 degrees case where you have maximum torque. I want to show you a more general situation, okay? So again, before we were thinking that the loop itself and the B field were just in the same exact plane, right? Now I want you to think about they can have any angle with respect to one another, okay? So this is a slightly different view of that same loop, okay? Just so we're clear. Now we're not looking at the loop like face on. Instead, we're looking at it from the top down, okay? So you're looking at it from this direction as opposed to face on like before. You're looking at it from the top down. And if we take that view, that top down sort of view, here's what it now looks like. See that force F2 is now going like this, straight down. That force F4 is going straight up like this. And our axis of rotation is now going into the page like this. So the y direction is now out of the page like this. This is the x direction. This is the z direction in this new point of view. Okay? And unlike before, where we just had our loop exactly lined up with the B field lines, we're just going to let them have any arbitrary angle with respect to one another. And we're going to call that theta. Okay? So hopefully you can see right away, right? Like my R vector from the axis to the force is like this. It doesn't make a nice 90-degree angle anymore, right? In general, it's just some random angle, theta. So the way we want to think about this is our torque, which we found the maximum of before, is going to get modified by a factor of sine theta. It's going to be reduced by a factor of sine theta. So what we can say is the torque is what we found before, I times A times B. That's the maximum value. If we multiply by sine theta, that's a more general expression. Okay? There's one other thing that we want to keep in mind too. So far, we've been imagining that for our loop of current, there's just one turn of wire. So basically, you just take the wire, you wrap it around, and you reconnect itself up here. In general, you can wrap the wire around many times. I can make a coil of wire where I wrap it around, let's say 50 times or 1,000 times. And each one of those wrappings of wire feels its own torque, okay? So if I wrap it around twice, I get double the torque. If I wrap it around 5 times, I get 5 times the torque. So in general, if we say there are n turns of wire in our loop, we're going to multiply that torque by n. And this is really important because in general, let's say I'm dealing with like an electric motor, I'm going to have many, many wrappings of wire, not just one, right? Because we want to amplify that torque. All right, so here's what we have. For n turns of wire, the torque on a loop of current is n times I times A times B times sine of theta. Let's review all these terms. N, again, that's how many times we've wrapped that coil of wire around. I, that's the current that's running through that wire. A is the area of that loop of wire. B is the strength of our B field, and sine of theta is the angle between our loop of wire and the B field. Okay, so all of these factors actually have to come into play to get the torque. Okay, so hopefully you're seeing where this is coming from. Any questions so far?
Right. I said B was what again?
That's just the strength of the magnetic field. Yeah. How strong the magnetic field is. So yeah, in Tesla is how we typically measure that. Okay, so now that we've kind of worked out this messy expression, I'm going to show you a way to write it in a more compact way. That's more general, that you can apply to any situation. Again, it's not just about this specific rectangular loop that we were looking at. It can really be applied to any situation. So in general, the torque on a current loop in a magnetic field is given by this. Since we have that sine theta factor, you should be thinking that kind of looks like a cross product, right? If I have two vectors and then sine of the angle between them, that's pretty much what a cross product is. So it looks like we can write this in terms of a cross product. So tau, the torque, is given by n times I times A. Now I'm going to think of A as a vector, so I'm going to explain that in a second. Crossed with B, where B is our B field, and of course the B field is a vector. It has a direction to it, right? All right, so it should be pretty straightforward to think of the B field as a vector with a direction. Area as a vector with a direction. We've seen that before, actually, right? Remember in Gauss's law? E dot dA, where A is a vector. We're doing something quite similar here. So the way it works for the area vector, if we want to understand what direction this guy is in, we use a right-hand rule, okay? So you take your current loop, and you take the fingers of your right hand, and you curl those fingers in the direction that the current is flowing, okay? And of course, the current goes in a loop, so just curl your fingers in the direction of whatever that loop is. Then your thumb is now pointing in the direction of your area vector. That's just how the convention works, okay? So as an example, let's say this is my loop, and I have the current flowing this way around the loop, all right? I'll take the fingers of my right hand, curl them in that direction, and now my thumb is pointing straight out of the loop like this. If I took that same loop and I faced it this way, now that would be my area vector. Facing this way, now that's my area vector. Make sense? Okay. And sometimes we try to write this in an even more compact way. There's nothing really special about this next move I'm going to make. It's just to take this n times I times A thing and just combine it into one term. We call this thing the magnetic dipole moment. This is going to come up in the next chapter. It's kind of an important concept, but for now, let's just think of it as this quantity, n times I times A, where again, we're thinking of A as a vector, so this also has a vector, it has a direction to it, and we use mu to denote that quantity, okay? That's the magnetic dipole moment. So if this whole thing in front is just going to be called mu, then we can say that torque is just mu cross B. A much simpler way to write it, okay? So In summary, you have a loop that has some current running through it inside of a magnetic field. If you take the magnetic dipole moment of that loop, which is defined like this, you cross it with the B field, then you get the torque, okay? Now I know actually calculating this can get confusing because you have so many right-hand rules to apply. So we are going to go through some examples of that to make sure we got it down, okay? So here, let's try this one, okay? You have, remember this result, the torque on a loop of current is equal to mu cross B. All I want you to think about for this part is the direction of the torque. I don't even need you to calculate anything, just tell me what the direction of the torque is. So you're gonna have to do two things. You're first gonna have to find out what's the direction of mu. That's our dipole moment vector. There's a right-hand rule for that. Remember, you curl your fingers in the direction of the current. That gives you the direction of mu. Then once you have that, you're going to do mu cross B. That's a second right-hand rule to do the cross product. But once you have that, you'll have the direction of the torque. Okay? So two right-hand rules to get the direction of the torque. All right? So in this situation, our B field's just going straight to the right. We have four different loops to work out, okay? In the first case, you're seeing the loop face on, and the current is going this way. In the second case, you're seeing the loop edge on. So to be clear, what's happening is the current is flowing like this. That's what this arrow is representing. You're seeing the side closest to you with the current going up, the side furthest away from you, the current's going down like this, okay? With this one, we're seeing it face on, that's our current. This one, we're seeing it edge on. So the side closest to you, that's the current. That means it's going like this, all right? So take a few minutes, try to work these out. Again, you're gonna have to be using the right-hand rule, so I should see you doing all kinds of stuff like this, right? So what I would try doing is, again, work out the direction of the mu vector, draw that on your page, and then do mu cross B. Once you see what the directions of the mu and the B vectors are, you should be able to get the cross product. This is reframe right there. All right, let's try the first one, okay? Let's do it together. How do we get the direction of the mu vector? We take our right hand, and we curl our fingers around in the direction that the current is flowing. And then our thumb is now pointing in the direction of mu, okay? So which way is the mu vector going in the first picture?
Into the page.
It's going into the page, right? Do this, the thumb is going into the page. Now, I have to take a vector going into the page, cross it with the vector going that way, okay? So here, start off, I have to point the fingers of my right hand into the page. That's the direction of my mu vector. Then I have to curl them going that way, the direction of the B vector. Where's my thumb?
Negative y.
It's going down. Negative 1. That means this current loop is going to be induced to rotate this way. Okay, you see that? That's the type of rotation that's going to happen in this scenario. Right? How about the second case?
I got mu's in the negative x direction.
Yeah, so here, what you should be thinking about is curling your fingers like this. Okay, does that make sense from the picture? Because this is the side closest to you, that's where the current's going up, but it goes all the way around like this. All right, so you're right. Looks like my thumb is in the negative x direction. So what's mu cross b going to end up being?
0.
Zero torque for this guy, that's correct. Because if I take a vector that's pointing that way, and I cross it with a vector that's pointing that way, they're at 180 degrees. And for a cross product, if you have your two vectors at 180 degrees or 0 degrees, either way, you're going to get 0 as the result. Okay, so minus y, 0 are the first two. So try to work out the next two given what I just told you. Okay? Who's got number 3? What are we getting?
Positive y.
Positive y. All right, this one, let's do it on paper. All right, let's just work it out in gory details. So this is number 3 from that set of examples. Okay, so in this case, we have our B field going like this. So this is what I suggest. If you ever have to work something like this out, is just draw every single vector on the paper, and it should be pretty straightforward. Okay, my loop is being seen face on like that, but we see the current being carried like this in the counterclockwise direction. So here, let's figure out the mu vector. That's going to be like this, out of the page. Do we agree? As I curl my fingers this way, my thumb ends up out of the page. So I'm going to show mu like this. And I know that I need to do mu cross b. Okay, so let's do that. Looks like mu is coming out of the page. So I'm going to point my fingers on my right hand right towards you guys. And then B is going that way, so I have to curl it that way, to the right. Yep, thumb's going up, huh? So that's the positive y direction, going up. So I'll draw the torque vector. That's our torque, it's going up. What does it mean to have a torque like that? It means we're being induced to rotate like this, okay? That's our rotation. So if you take a loop, run the current this way, in this type of B field, that's the type of rotation that's going to start to happen. Okay? Any questions on that?
So if it was pointing down, the rotation would be opposite, correct?
Yeah, and that would be the first example we did. Okay, let's do the fourth example. Okay? So let's work out what is the direction of the mu vector.
I got negative y.
Yeah. I don't know if you're doing that to me or you're trying to tell me this is the mu vector, but anyway, yeah, curl this way, right? That's our mu vector. In the direction of the current, our thumb points down when we curl our fingers in the direction of the current. Okay, so let's work it out on paper. Again, we have our B field going this way. We have our current going like this, which means our mu vector is pointing straight down like this. So yeah, number 3 we got down, right? In this case, what do we get when we do mu cross b?
Out of the page.
Yeah, it looks like that's right. If I do mu cross B like this, my thumb ends up pointing out of the page. Okay? So now my torque vector is out of the page like this. So here, torque, which is mu cross B, ends up going out of the page. So again, let's remember what it means for torque to be out of the page. That means the direction of our rotation that's induced is like this, okay? So again, it's not all that obvious. You have to kind of do it in steps. It's hard to just sort of look at the picture at the beginning and immediately know what the torque is. So again, figure out where your mu vector is, then do the cross product. If you take it in those steps, you should be able to get it, okay? So there's our rotation. So there's our spinning loop rotating this way. Go ahead.
Or number 3 was up, right? It wasn't that.
Oh, did I say it was down? I wrote that it was down, but yeah, we said it was. Yeah, so it was up. Yeah, sorry. Yeah. So all this work is correct. I just meant to write that. Okay. Okay. Anything else? All right. So now we know how to deal with torque. Let's do a few more things that have to do with torque. So in this one, we're going to make some calculations. We're not simply going to, just work out the right-hand rule to figure out directions. Okay, so we have a circular loop. This has a radius of 12.5 centimeters. And it has 10 turns of wire. So we're going to take 10, we're going to go around that wire and wrap it around the circle 10 times. Okay, that's what's going on. We're going to run a current of 1.65 amps through the loop, and we're going to put it in this magnetic field where the B field strength is 0.175 Tesla. We see that the plane of the loop here is at 35 degrees with respect to the B field lines, okay? And we're seeing it edge on like this. So the question is, let's calculate the magnitude and the direction of the torque that's acting on this loop, okay? So just like before, we're going to start with the direction. And again, when we see a loop edge on like this arrow is trying to tell you that the side that's closest to you has a current going this way, okay? But what you should be thinking is the current is actually circulating like this around the loop. Does that make sense? Okay, so let's do, using the right-hand rule, the direction of mu. So we're going to curl those fingers in the direction that current circulates around the loop like this, okay? And then my thumb is pointing in the direction of mu. So that's pointing that way, kind of into the fourth quadrant, down into the right like this. Make sense? Okay. So I just wanted to establish that basic picture. Now we're going to draw a diagram, put some more detail on it, and allow us to do the calculation. All right. So the first part of this is just copying down what we've already seen. Here we have this loop, which we see edge on, with current I running through it. It's inside of a B field. And the B field lines are just going straight to the right like this. Okay, we have an angle right here, which we're given. We don't know yet if that's the angle we need to do the calculation, but let's just label the angle. That's 35.5 degrees. Okay, that's between the plane of the loop and the B field. But what we said is the mu vector is going like this. This is our magnetic dipole moment vector mu, okay? Now, the thing about this vector is it's perpendicular to the surface of the loop, right? So there's a right angle right there. It's important to note that. What is this angle right here between B and mu? Yeah, so I'm going to call this guy theta. That's the angle we're actually interested in. I'm interested in the angle between B and mu because I'm crossing those vectors, okay? That's 90 minus 35.5 degrees, which equals what? 54.5, yeah. So actually, that's the angle that's going to be relevant in our calculation, okay? So let's start. Since we have to calculate torque, let's just write it as a cross product. And by the way, this is kind of how I approach all cross products is, you know, we can split it into two parts. There's the magnitude of it, and then there's the direction. The direction is found by the right-hand rule. So let's do that first. Direction of our torque. Well, I have to take mu cross B using my right hand, okay? I have to get in the right position to do this, but basically, mu is my first vector, so I'm going to take my right hand and point it like this in the direction of mu, and then curl in the direction of B, just that way, and now my thumb is out of the page. Do we agree? So it looks like the type of rotation that's going to be induced in this particular coil is this. It's counterclockwise from our perspective. Right? So torque ends up being out of the page. And if we draw that torque vector on our diagram, again, going out of the page, it's meant to indicate that the rotation is like this. That's counterclockwise. Okay? Now for the magnitude. Okay, magnitude is not too hard. It's a cross product, so just like every other cross product we've seen, magnitude is magnitude of the first vector, which is mu, times the magnitude of the second vector, which is B, that's our magnetic field, and then sine of the angle between them, which is what we worked out over here. But one more step we should remember, because mu, if you recall, that's just a shorthand way of saying N times I times A. That's what it means. N is how many turns of wire we have. That's 10 in this case. I is how much current we have running through the loop, and A is the area. Okay? So really, I can write this as N times I times A times B times sine of theta. And that's what we worked out before, by the way. But I'm just showing you that usually we write it in this more compact form, okay? So let's put in what we know. N is exactly 10 turns. I, that was 1.65 amps. For the area, that's going to be basically a circular area, pi r squared. So for the area, I'm going to take pi times our radius, which was 12.5 centimeters or 0.125 meters, and square that. So that's the area. And then we have B, 0.175 Tesla. And then we have our sine theta factor, which is sine 54.5 degrees. What does that give us?
We got 0.115.
0.115 Newton meters. That's how much torque there will be, 0.115 Newton meters. And again, the direction, we've already worked that out. Make sense? Any questions? All right, let's do another, yeah, go ahead.
When you say that N stands for the number of turns for the current, is it like a spiral of it, or is it?
Yeah, so we're actually going to build loops like this in an upcoming lab, so you'll see more clearly then. But imagine, okay, I wanted to build this type of thing, right? I could take like a cylinder, let's say, and just wrap the wire around the cylinder. That's 1 turn, 2 turns, 3 turns, and as many as you like. So that coil of wire has a circular shape to it, right? And it's just how many times you've wrapped it around. Okay? And it makes sense because the more times you wrap it around, the more we're sort of amplifying the torque, because each turn feels its own separate torque, right? That's why in actual motors and generators, you don't just have a single loop of wire. You have like many, many, many turns to amplify the torques. Go ahead.
So is that the torque that the loop feels, or if you were inside of the loop?
That's this right here, this is the torque that the loop will feel. So this directly relates to how the loop will start rotating, okay? Just keep that in mind. Torque induces rotation. So this torque can cause rotation to start happening. So this is exactly what would be going on inside of an electric motor, let's say, which we will get to later in this lecture, okay? All right, so let's do one more. So we'll do this example. That's the last example on torque that I wanted to go over. Then we're going to talk about technological applications, one of those being the motor, another being loudspeakers. And after that, we can have time for a couple examples. All right, so that's what we'll do today. So here's what's going on in this example. There's one like this on the homework, so pay attention. We have a loop with 10 turns of wire, and it's shaped like a square. And the side length of that square is 12.5 centimeters. The loop itself has a mass of 0.456 kilograms. And let's assume that its mass is evenly distributed so that the center of mass is right in the middle of it. This is going to become relevant, as you'll see. All right, we're going to take this loop and suspend it from strings so that it can hang horizontally like this. Okay? But suddenly, we turn on a magnetic field. And in this case, we're going to imagine the magnetic field is going to the right in this picture where we see the loop edge on. Okay? Now, because of this magnetic field, the loop starts to experience a torque. And that torque causes it to go from just hanging this way to being in this horizontal position. Okay? All right, so what's happening basically is there's a magnetic torque and then there's a gravitational torque. Gravity tends to make it want to rotate back down to here, but the magnetic torque makes it want to rotate this way. If they're perfectly balanced out, they can just hang like this in that position. Does that make sense? So if you have these two torques balanced out, it can hang like this. Okay, so the question is, how much current must be running through the loop in order for this balance to happen, okay? You can imagine if there's too little current, there won't be a big enough torque from the magnetic field to get it up to this point. If there's too much current, then it'll just start flying around, right? So there's some kind of sweet spot where we can just balance out like this, okay? So any questions on the setup here? Hopefully that's making sense. Okay, so here's what we'll do next. We will draw a picture of what I just showed you, where we have this string hanging down like this, and we attach that string to our loop, which has current running through it, and we want to look at the situation where it's balanced in this horizontal position. The B field is going to the right like this, and the current is going to the left like this on the side of the loop that's closest to us. But remember, we want to imagine that the current is circulating around in a loop like this. So let's go ahead and find the mu vector on this diagram, okay? We're going to take right hand, we're going to curl it in the direction that current is circulating around the loop, so it's like this. My thumb is now pointing down. Does that make sense? Thumb is going down. That's the direction of mu. And to get the torque, and in particular, I'm not just going to call this tau, I'm going to call this tau B. That's a magnetic torque. Okay, it's the torque from the magnetic field. That is going to be equal to mu cross B. All right, so what's mu cross B? Mu cross B is, take your right hand, point your fingers straight down in the direction of mu, and then curl them to the right in the direction of B. Which way is my thumb going? Out of the page, right? So my tau B is out of the page, which means the magnetic field is trying to make the loop rotate this way. It's trying to bring it upwards, right? That makes sense? And that's what's working against gravity, by the way, because what gravity's trying to do is bring the loop downwards. That's why they can balance out, okay? But anyway, let's put a number to this guy. The magnitude of this torque is equal to magnitude mu, magnitude B times sine of the angle between mu and B, which is what? That's a 90-degree angle, right? If you got B going to the right and mu straight down, they make a 90-degree angle, right? With respect to one another, so we have sine 90, which is just going to give us a factor of 1, right? So we could just neglect that from here on out. Okay, let's also remember that mu is n times I times A, and then we have B, and then sine 90 just became 1. Okay, let's do one more thing here. The area of my loop, A, it's a square, right? So what is the formula for the area of a square? It's just the side length squared. Let's call that side length L, and we're going to square L. So in total, what I have is N times I times L squared, that's what I'm subbing in for A, times B. Okay, there we go. I'm just going to leave it at that for now. All right, so that was the magnetic torque. Now let's work out, so let's just put up here, we're doing the magnetic torque for that work that we just did, okay? Now let's work out the gravitational torque. Because its own weight, again, is going to induce a torque on it. Let's work that out. So same picture, I have the string right here. I've got the attachment point there, and then I have the loop going like this. And here's where the center of mass is important. We said that because it's sort of like evenly distributed mass, that the center of mass is right in the middle of the loop. So they're marked with an X is our center of mass. Okay, now for this torque, here's how I want to think about it. I have a force of gravity, which goes straight down, okay? Fg. That's the gravitational force. I hope you guys remember from Physics 45 that the force of gravity effectively acts at the center of mass. That's what we're showing right now, okay? So then, since this is our pivot point, the r vector is going to go from that pivot point to the center of mass. So we don't have like a special formula here. We're just going to go back to the basics. Torque equals r cross F. Okay? That's how we're going to work out this torque. So I'm going to call that tau g for the torque due to gravity. That's going to be r crossed with Fg, which is our force of gravity. All right? Good so far? Let's just real quick verify the direction of that torque. We're going to do R going this way from the pivot point to the center of mass. Cross F, that's our force going straight down. That's into the pitch, right? So that's in the exact opposite direction as our other torque. So this is going into the page. And if we draw that torque going into the page on our diagram labeled tau g, this torque makes our loop want to rotate this way. And so we have these two opposing torques. They balance each other out. That's what I was claiming before. So hopefully you see it now. All right, for the magnitude of this torque, that's going to be magnitude R, the magnitude of our gravitational force, and then the sine of the angle between them. But what is the angle between them here?
90.
Yeah, this vector and this vector are 90 degrees. Which gives us a factor of 1. And by the way, R is just going from the edge of the loop to the center. So it's half of the length. L over 2 is another way of expressing R. You see that? How do I express the force of gravity? So that looks like it's just L over 2 mg, and then sine of 90 gives us 1. All right, so we have a half L mg. That's our gravitational torque. So would you agree that if this thing is just static and not rotating at all, that this torque, due to the magnetic field, has to equal, at least in terms of the magnitude, this torque? The torques balance, which means the magnitude of tau b equals the magnitude of tau g. That's what we're doing next. Got it? So let's just plug in what we know. For tau b, we have ni L squared b. For tau g, we have half L mg. What were we trying to solve for in the first place? The current, right? We're trying to say how much current is it going to take to get this to all balance out. So let's solve for I. All right, if we solve for I, we're going to get m times g is on top. We have a factor of 2 on the bottom. And then I'm going to have a factor of n on the bottom and a factor of L on the bottom. The L squared, one of those is going to cancel with the L here. And then we'll have B. We agree? Okay, so plug the numbers in. This particular loop had a mass of about 0.456 kilograms. And G, what's the value? 9.8 meters per second squared. We're going to divide by 2 times n. We have 10 turns, so 10 turns of wire means n is equal to 10. Then we have the length, L, of each side, which was 12.5 centimeters or 0.125 meters. Remember, you want to get everything in the SI unit before plugging things in, so that what you get out has SI units. I think that's the best way to go. Okay, then B, what was that? That was 1.25 Tesla. So, can someone work this out for me, what it comes out to?
1.43 amps.
Yeah, it's going to take 1.43 amps of current for this to work out. Okay? Do we have any questions on this one? So, yeah, I think, each step is probably not so bad, but a lot of things have to come together. And it's, of course, pretty easy to make a sign error with all these different right-hand rules. So, let me know if you have any questions about this one. If not, we'll move on to the technological applications. Okay? So, we're going to look at 2 cases in particular. One of them is the electric motor. Obviously, a very important piece of technology. I'm going to explain to you how it works in a nutshell. Okay? So let's start with the electric motor. Now, big picture, what is the physics principle behind the electric motor? Why is it that electric motors work in the first place? It's because if you have a magnetic field and you put a loop of current inside of that magnetic field, as we've just seen, the magnetic field exerts a torque on that loop. Okay? So basically, if we can take 2 very strong magnets, like put a north and a south magnetic pole right here, and put a loop which can carry some current in between those 2 poles, well, guess what? We're going to have exactly what I described. We're going to have a loop of current in a strong magnetic field. So what we do is we run some current through that loop. We can easily do that by just connecting the loop to a battery, right? That would be a DC motor, by the way. If we just connect our loop to a battery, you're going to have direct current flowing to it, and in which case you'll have a DC motor. So again, this loop is going to have a torque exerted on it. That torque can cause it to start rotating, okay? And if we can design this thing in a way where it just has a consistent torque that's always causing it to rotate in the same direction, then we can sustain that motion. We can just keep it rotating as long as the current keeps flowing. You see that? But there is a little bit of a complication here, okay? So what's not going to work is I can't just take this loop and connect it to a battery, put it in this strong magnetic field, and then say I'm done. The problem with that is the torque actually is going to reverse direction every half turn if I just have the current going in one direction and one direction only, okay? So if I have the current only going in one direction and never changing, every time the loop gets to this vertical position, the torque is going to flip around and go the other way. So instead of just rotating, it's going to just kind of slosh back and forth like this. That is obviously not what we want a motor to do. We want it to just rotate in one direction and maintain that rotation for as long as possible. So to make sure we get that, we use something called a commutator, okay? But before we get to that, I just want to sketch out a picture that will hopefully convince you that this is the case, okay? That we can't just have a loop with current going in one direction all the time and get a steady torque. It's not going to work. So here, let's take a look at this picture. All right, so I'm going to imagine that we have the south pole of our magnet, the north pole of our magnet like this, and then we have our B field, which basically goes straight across from the north pole to the south pole of our magnet. Then I'm going to imagine that we have our loop, which we're seeing edge on, okay? And for this illustration, let's just say the current in that loop is going like this, okay? Okay, and let's also say that it's rotating in this direction, okay? All right, cool. So, I know that the torque that's going to be experienced by this thing is equal to mu cross B, right? So we better figure out what mu is in this picture to figure out what kind of torque our loop is going to be receiving, okay? What's the direction of our mu vector? Oh, okay. Curl your fingers in the direction of I. It's kind of going down and to the left, right? Or, sorry, down to the right like this. Do we agree? That's our mu vector? Okay, so guess what? Now we have to do mu cross B to figure out what kind of torque we're going to be feeling. So we got mu like this, we got B like this. Looks like my thumb is into the page, right? So it looks like my torque's going this way. Okay. Now, since we're imagining the coil passes through this vertical position, now it's going like that, okay? And let's say we have not yet changed the direction of the current, so our current is still going the same way as before, okay? All right, so what direction is our mu vector pointing now? It's going to be, curl your fingers this way. My thumb is kind of going up and to the right at this point. And if we go ahead and do mu cross B, oh, thumb's coming out of the page. That's what I was trying to tell you before, right? If we just only allow the current to flow in one direction, the torque is actually going to flip when the motor goes over the top, okay? And I hope it's clear, you do not want a motor to do that. For a motor, you just want the torque going one way. You want consistent, steady torque. If the torque flip-flops back and forth, that's not going to cause rotation. That's going to cause the coil to flip-flop back and forth, okay? So how do we fix this? We need the direction of the current to flip when the coil goes over the top like this, okay? And the way we can cause that direction to change every half turn when the coil goes over the top is to use something called a commutator, okay? This right here is a picture of a commutator. It's what's connecting our coil to the battery, okay? So basically, if you kind of follow along, this part of our coil is connected to the battery right here, and this part of our coil is connected to the battery right here. But when it makes a turn, now we're going to be connected to the opposite ends of the battery. Okay, so we're sort of like flipping our positive, negative connections every half turn with the use of this commutator. And that allows the current to flip, which is exactly what we need for steady torque, okay? So a DC motor, which runs off a battery, is going to have to use some kind of commutator to actually produce a steady torque. Another way you can do it, by the way, is AC current, because AC current already flips back and forth in the way we need it to, okay? So, yeah, that's just something to keep in mind as far as motors go, right? You need some mechanism of flipping the current. So I'm going to show you an animation of this exact sort of thing. You see how the commutator works? It changes how we're connected to the battery so that every half turn, the current flips. And if we flip the current every half turn at the right moment, then we can get a steady torque. Any questions on what you're seeing here? All right. So you can look at this animation through this link here. It's on the slide. Okay. There are tons of other technological applications, but one of them I want to show you is a loudspeaker. And before we even get into this, I want you to keep in mind this is super general. It's not just like the loudspeaker you find in your car or in a home stereo system. It's also the tiny speakers inside of a laptop computer or even in headphones. Fundamentally, they all kind of work the same way when we're looking at it from a big picture perspective. Of course, each one is designed slightly differently. There are different ways to design a loudspeaker. But fundamentally, this is what's going on, okay? This is the physics behind it, okay? So thinking about this like a physicist, what's the principle behind a loudspeaker? Well, the basic principle is if you have a wire that has some current flowing through it, and you put that wire in a magnetic field, we know that there will be a force acting on that wire, okay? That was the very first thing we learned in this lecture, right? You put a wire that has some current flowing through it, you put that in a magnetic field, and then it begins to feel a force, okay? So here's how a speaker is typically designed. We have some kind of magnet or set of magnets which is producing our magnetic field. And we take what's called our voice coil. This is just a wire wrapped into a coil many, many times around that magnet, okay? So that coil obviously is in the presence of a very strong magnetic field, okay? Now, we can run some current through that coil, right? And of course, if we're trying to play some sound with the speaker, this is not going to be just direct current. This is going to be an alternating current. It's going to be a very complex alternating current because it has to carry all the information about the sound wave that we're trying to produce, okay? So for example, if I want to play a sound wave out of the speaker with a frequency of 200 hertz, I better be running some current through this coil with a frequency of 200 hertz. If I want some incredibly complex set of frequencies that you find in like a song, well, I'd have to have all of those frequencies present in this alternating current, okay? So basically, information about the sound you are playing is in this alternating current. All right, so we run that current through this coil. Now it starts to feel a force, okay? And because we have alternating current, it's going to be the type of force that makes it go back and forth. It's going to make it vibrate back and forth with whatever frequency we sent into the coil, okay? So again, if I send a 200 hertz signal into the coil, this is going to start vibrating back and forth at 200 hertz. Now, this coil is connected to something called a cone. And you probably have seen these in larger speakers. You can see the cone. It's usually behind some kind of protective mesh, but basically this cone is now going to start moving back and forth at the same frequency as the signal, okay? There's air right here touching the cone. The cone is just pushing that air back and forth with whatever frequency we originally sent in there. And that's going to produce a sound wave with whatever frequency we originally sent in there, okay? So if we have alternating current with a certain frequency, it causes mechanical movement of a certain frequency, which produces a sound wave of a certain frequency. And that's basically the principle behind any sort of speaker or headphone or anything you like.
So when they blow out, is it because it's not enough, it's too much current and it's not enough wire to extend it or what?
Yeah, so you can definitely blow out a speaker by running too much current through it. If you crank up the current, generally that's going to create larger forces and louder sounds as a result. So yeah, the electronics might only be able to withstand a certain amount of current. You might blow, depending on how it's designed, you might blow a fuse or something. Yeah?
How can you mess with the quality of sound that comes out?
Well, that's going to be really complicated, but basically a lot of it will have to do with the mechanical properties of this coil. So, because again, I'm kind of oversimplifying. I'm saying, let's imagine we just have a single frequency that we're playing. If you're listening to a song with a bunch of different instruments, there's going to be a huge range of frequencies that we want to be accurately represented, by our motion of this cone, right? So it turns out certain shapes and sizes respond better to different ranges of frequencies, which is why on a really good sound system, you're not just going to have one speaker. You're going to have subwoofers with giant cones to play in the low bass register, and then you have these tiny little tweeters that have tiny cones that have the nice high frequency response. So you kind of have to just mix everything together because different components might have a better response in certain frequency ranges.
Does a microphone have opposite?
Yeah, that's a great insight. We're going to talk about that later, but essentially, let me talk a little bit about that. This is a bit oversimplified, but essentially a microphone is just this process run in reverse, okay? So instead of current coming in, creating motion in this cone and sending a sound wave out, instead you have a sound wave coming in, creating motion in the cone, and then inducing current to start flowing. And you can record that as a digital file or whatever, or play it out of the speaker. Right? There's all kinds of different things you can do to mix and match speakers and microphones. But a microphone is more or less this run in reverse. By the way, what do you get when you run a motor in reverse? So instead of running some current and you get rotation out, you try to rotate it to get some current out. What is that called?
Generator.
That's called a generator. Yeah. So a generator's in a lot of ways just like a motor running in reverse. Okay, so here's an animation of a loudspeaker. Again, we have that alternating current flowing into the coil, which is in the presence of this strong magnetic field, so that causes the coil to experience a force, which vibrates this cone up and down at the frequency we want it to play whatever sound we want it to. Okay? That's the idea. All right, any questions on this? That's pretty much it for the technology stuff. So we will spend the last maybe 25 minutes going through some examples. I think it might be good to go back to this, the helical motion of a particle in a magnetic field. We did one of these examples in class, but honestly, there were a bunch of people yelling outside at the time, if you remember, and I think maybe I didn't get the point across. So I think it'd be good to go through this again. So we have an electron here, and we know the mass and charge of an electron. We're going to put this electron into a magnetic field, and we'll start it off with the speed of 1.3 times 10 to the 7 meters per second. But we'll make it come in at an angle of 35 degrees relative to the B field line. So our velocity of the electron is like this. Our B field is like this. There's an angle of 35 degrees between them. The strength of the B field, by the way, is 0.0150 Tesla. So the question is, we already know what the motion is going to look like. We know that it's going to move in a helical pattern, okay, in a spiral. So what you're going to do is find the radius of that spiral and the pitch distance, which is the distance between each loop in the spiral, okay? So remember, here's what I would suggest that you do. Start by breaking this velocity into V parallel. This is the component that goes along the B field lines, and V perpendicular, which is perpendicular to the B field lines, okay? Because of the way magnetic forces work, it's QV cross B, if you recall. There's not going to be any force in this direction, right? There's never a force along the B field lines because it's a cross product, right? So that means this motion is at constant velocity, okay? But the motion in the plane perpendicular to the B field lines, so if I were to look down the B field lines like this, straight into them, I would actually see circular motion. It's kind of like it's moving in a circle, but the plane of that circle is moving at constant velocity along the B field lines, okay? So try to just break it into those two motions. It's kind of too complicated if you look at it all at once, so if you break it into these two motions, it might make it a little easier to see, right? So try to work it out, and we'll go through it. Let's start with the radius at least. And, let's get the radius. Raise your hand and I'll check and see if you guys are right. So plug in the numbers there, you should get it. Got the radius. Looks good. let's start by going over the radius part, everybody. Does anyone have an answer for this? It's in millimeters.
2.8.
Yeah, something like 2.8 millimeters would be the radius of these loops. So it's a pretty tight spiral. Let's see how that works. So basic picture is right here. We have our v field and we have our velocity vector. And they're not, at a perfectly 0-degree angle or 90-degree angle. There's just an angle theta there. And so what we can do is break it up into v parallel, going with the v field lines, and v perpendicular, okay? So let's just remember the sines and cosines. What should I get for v parallel, just symbolically?
V sine theta, or cosine theta.
Yeah, so this is the adjacent side. So v parallel is the speed v times cosine of the angle theta. V perpendicular, that one goes with sine, right? Okay? So now what I want us to do is take the perspective looking into the v field lines. So imagine your eye is basically here, and you're looking that way, okay? From that perspective, here's what you'll see. You'll see the v field coming right at you, right? You'll see the v field coming out of the page like this from that perspective. And you will only be able to see this component of the velocity v perpendicular, which in this case looks like it's going straight up. Does that make sense, everybody? Okay, so, what kind of force exists when we have a charge moving with some velocity in a v field? It's qv cross v. But remember, it's only v perpendicular that contributes anything to this force, okay? Okay, so let's work out the right-hand rule for this guy. We're doing v cross b. We're doing v like this, crossed with v like this, except I have a negative charge, don't I? So just flip that. I'll show the force acting on my particle going this way, which means the circle that we see, I'm just drawing some of it, looks like this. That make sense? Because remember, the force is always going towards the center of the circle. That's how I know to draw the circle this way. All right, we're good on that? So let's do F equals ma in the radial direction, because that's how I analyze the circular motion that I see in this plane. So, looks like the force is just the magnitude of this guy. That's going to be Q, and then we have V perpendicular, okay, times B. And then looks like if I'm just considering V perpendicular, that's going to be at a right angle to B, because V perpendicular is like this, B is like this, right angle. So I'll write sine of 90. Again, between these two vectors. And that equals mv squared over r. Well, again, it's only V perpendicular that's participating in the circular motion. V parallel, that's just going in a straight line like that. So we have mv perpendicular squared over r. That's just the way we define the centripetal or the radial acceleration, right? So v squared over r. But it's only applying to V perpendicular. Okay? So therefore, if I'm trying to find the radius, looks like that radius is going to be mv perpendicular divided by qb, which if we go back to the top, v perpendicular is the speed of our particle times sine of that angle, theta, okay? So now we have mv sine theta over qb, and we're ready to calculate what this radius is, all right? So let's do it. What's the mass of an electron? Was that n term? 9.11 10 to the minus 31 kilograms. V was 1.3 10 to the 7 meters per second, and sine of 35 degrees was what we had for this problem. All right, then charge. Here we're strictly speaking magnitudes. That's 1.6 10 to the minus 19, because over here we found the magnitude, right? So this is positive by definition. Coulombs, the B field, 0.0150 Tesla. Okay, there it is. So yeah, what do we get? We get 0.00283 meters, which you can write as 2.83 millimeters. That's the radius of this helix, okay? So the next thing we want to do is find the pitch distance, okay? Pitch distance, remember, is the distance between the loops. So the way that we go about doing this is to first find the period, okay? Because remember, the period is how much time it takes to make one loop. The pitch distance is how far you've traveled along the B field lines after making one loop. In other words, it's how far you travel along the B field lines in one period. Does that make sense, everybody? Okay. So here, let's work it out. I'm going to write down just a basic like speed is distance over time type formula. And I'm going to apply it to both V parallel and V perpendicular. That's, to my mind, the easiest way to come up with the relationships, okay? So for, let's say, V parallel, right? The distance we travel is the pitch distance P, and the time it takes is the period. Make sense? Meaning the pitch distance is V parallel times the period T, or we go to the top of the page, V parallel was V cos theta. So it's the speed of our particle times cosine theta times T. That's our pitch distance right there. But the thing is, we don't have the period. So we're gonna, we obviously have the V cosine theta part, but we need to find out what the period is to make this final calculation, okay? So the way we're gonna do that is to apply speed as distance over time to our other velocity component, which is V perpendicular, okay? Now remember, this one is referring to how fast the circular motion is taking place, okay? So what is our distance if we are talking about one period?
2 pi, right?
Yeah, in one period, we go around the circle one time. So our distance would be 2 pi r, and our period would be t. And we want to find a period, so t is 2 pi r divided by v perpendicular, like this, all right? And we could put a number to that. I could do this one of two ways. I could actually just put the radius that we just found right into this formula, because we know what v perpendicular is. Or I can make a substitution. I'm going to do it using a substitution. We found that the radius, if we go up here, was mv perpendicular over qb. So I have 2 pi divided by v perpendicular, and then for the radius, I'm plugging this guy in. I'm doing m v perpendicular over qb. Cancel out v perpendicular. The period is just 2 pi m over qb. You may remember we derived a frequency, which is just the inverse of that, okay? But that's where it came from, okay? So we have 2 pi times our electron mass, 9.11 10 to the minus 31 kilograms, divided by Q, 1.6 10 to the minus 19 coulombs, times B, 0.0150 Tesla. Can someone do that for me? What is that period right there?
2.39 times 10 to the negative 9.
Do we agree? I actually don't have this number in front of me, so Make sure that's the right period. We agree? Okay. Not that I don't trust you, that's the one, but just want to make sure. All right, so now we can plug that in to find the pitch distance, okay? Pitch distance P is, okay, V, I'm gonna just write it again, V cos theta times T, okay? That's what we're doing. Where V is 1.30, 10 to the 7 meters per second, cosine 35. And then T is 2.39, 10 to the minus 9 seconds. Okay. What's the result of that?
0.0255 meters.
0.0255 meters, or we say 2.55 centimeters. All right? So those are the results. Any questions on how we got that? So that's how you deal with a helical spiral of a particle going through a B field. So just to recap, this is like 2.55 centimeters for the pitch distance. That's how far apart each loop is from the next. This was 2.83 centimeters. That was the radius of the helix. Okay, that's it for today.